For today's agenda, we'll have a little introduction on vibrating wire technology and the strain gauge. We'll discuss some common applications that these gauges are used for. We'll get into the anatomy of the different vibrating wire strain gauges. We'll discuss some important pre-installation checks that we recommend when the gauges are received and before you install them. Then we'll get into surface mount strain gauges and the different variations that are available there. We'll cover embedment strain gauges as well. And then to wrap things up, we'll do a little discussion on understanding the calibration reports that come with these gauges. Just a little bit about Geocon. We have about 150 employees now. We were founded in 1979. We manufacture a various number of vibrating wire instruments, as well as a few MEMS-based options, such as inclinometers and tilt meters. We are officially employee-owned as of 2022, and all of our instruments are manufactured here at our factory in the US. Today's presenters are Rob Clark. So just a little bit about my colleague, Rob. He has more than 30 years of instrumentation experience in designing and installing an assortment of instrument types. Many of these years he spent in the consulting industry, where he served as an instrumentation specialist for a variety of small to large scale monitoring programs. He's worked in the instrumentation industry on many facets of the monitoring programs, ranging from development of plans and specifications through design and procurement of instrument systems, through to installation and monitoring, as well as the final product and presentation of data. He has installed over 100 inclinometer casings throughout his career, and he's currently working with Geocon customers, providing assistance for installation and in-house data valuation. A little bit about myself, Joelle Lang. I have over 12 years of experience with instrumentation through a variety of positions within Geocon. I advanced much of my knowledge on instrumentation, operation, and applications while working in outside sales for many years. I now serve as Geocon's training coordinator, collaborating with our instrumentation experts, such as Rob, to deliver training opportunities for those seeking to expand their knowledge on geotechnical instrumentation. And from here, I'll turn the reins over to Rob.
Thank you, Joelle, and welcome everyone to today's discussion on strain gauges. We're going to provide basically a brief, hopefully an hour-long presentation that basically is strain gauge 101, I would assume. So let's just dive into it. A strain gauge basically is a sensor or instrument used to measure strain, oddly enough, that's typically associated with an instrument device that's mounted on or within a structural element. This sensor, when fixed on or within the structural element, will provide an output that's relative to the applied force or maybe changes in the environment, such as temperature. This output can be used to determine changes in stress or applied force on that structural element. These strain gauges can be mounted externally, such as on a steel pipe pile, or embedded within the structure, like on the concrete girders or concrete pile. There's a variety of different types of strain gauges out there, that are commonly used, such as electrical resistance type or foil, fiber optic, and then vibrating wire. We're going to be focusing on vibrating wire strain gauges today, mostly because that's what Geocon produces. So, oops, I got carried away there. Hold on. So a little bit about strain for those that have forgotten your mechanics and materials from college days. Strain is basically a change in length over the length of an element. When this structural element is exposed to forces, including temperature changes, strains or stresses can develop. If this element is restrained on both ends, you will definitely get stresses develop in there. If it's not restrained, you'll only get changes in length, which would be strain. If these changes in strain or stress are within the elastic range of that structural element, there's a linear ratio between those two that's called the Young's modulus of elasticity. Knowing that modulus of elasticity and the stress that's developed, you can, if you know the cross-sectional area of that element, you can calculate the force that's developed either by the applied forces or the changes in temperature. Oh my goodness. There we go. So some of the applications that are strain gauges are used in are for tunnels. The strain gauges can be used in the tunnel liner to monitor radial or tangential stresses that develop from the overburden above the tunnels. Bridges, they can be used for monitoring for long-term structural health on either the girders or the supporting members of the bridge elements. Monitoring for conditions and changes, if you've got fatigue that's developing in some of the members, micro cracking that's being observed or experienced, strain gauges can be applied and see how things perform for long term. In piles, strain gauges can be applied either on steel pipe piles on the exterior, or like I said, embedded within the concrete for concrete piles or piers. The strain gauges can be put at various intervals to see how load distribution is played out within the length of that pile. Foundations, strain gauges can be placed in the concrete mass pours to evaluate the strains and stresses in there. Also within excavations, you can have strain gauges on struts to help monitor the loads of the struts to make sure that the loading isn't getting excessive. So lots of different various applications, many others that aren't mentioned here. So as we mentioned, we're talking about vibrating wires, and so we'll provide a little bit of a synopsis or summary of what vibrating wire technology is and how it works. So imagine it's like a guitar string, basically, the vibrating wire. You've got this string or wire that's supported at both ends, fixed at both ends, and like a guitar string, if you pluck it, you get a certain sound or frequency. With the vibrating wire, it's the same principle. So with a guitar string, if you change, and I'm not a musician, but if you tighten or loosen that guitar string, you're going to get a different sound and a different frequency. Similar to that of the guitar string, the vibrating wire, if those ends move in or move out, when that wire vibrates, you're getting a different frequency from it. So the idea is that we've got a plucking coil and a pickup coil that's centered on that wire. And once that coil is energized to pluck that wire, the pickup coil receives the vibration and the frequency and transmits that up through the signal cable to a readout or data logger. And that way you can determine from the calibrated values the change in position of that element. That's the basic rundown of it. So a little bit about the anatomy of the strain gauge. Basically, you've got the wire fixed from one end to the other with wire grips inside of a protective tube. And these end blocks are either secured with rigid connections to the structure or embedded within the concrete to provide some point of fixity later on. This protective tube typically has, if it's embedded in concrete, will have like a sleeve over it to provide a bond breaker. And then centered over the tube will be the magnetic and plucking coil assembly. And inside of that epoxy coated assembly is a thermistor also for reading temperature. So the leads from the thermistor and the coils are then routed up into the signal cable, which goes up towards the data logger and or readout. So once we put the clothes back on the strain gauge, it looks something like this. This is the standard model 4000 strain gauge. We're going to talk about this one a little bit later, and many other types of strain gauges. So what are some of the advantages of using vibrating wire technology, vibrating wire strain gauges? Typically, they're fairly rugged and reliable, and can be used in a variety of applications where you might not have the same sort of lifespan with electrical resistance. They can be used on driven piles and survive a fair amount of the dynamic forces applied by the pile driving. Obviously, when you get into pretty significant forces, you may want to have some redundancy in the installation of the strain gauges to help provide some assurance of survivability. Also, they're very stable for long term. Vibrating wires have been shown to provide significant or not changing output for quite a few years. We've got some sensors in the Geocon facility that have been read since the early 80s, shown here on this plot, with very little, if any, trend or drift over time. And we've got some case histories from installations that have been done for almost 40 years where there's been very negligible drift over time as well. Some of the other benefits of vibrating wires is that you can run the signal cables for long distances. Not that you would necessarily want to, but we've done tests in-house where we've had signal cable run for 2 miles without any degradation of the signal from it. The cables can be easily spliced without affecting the performance of the signal as well. And if moisture does get onto the signal leads, it's not an issue unless that moisture does transmit up through the cable into the sensor. But we have had instances where the cable leads are set in a pool of water and you pull them out, shake them off, and take readings, and it's all fine. They're also, vibrating wires are pretty easily data logged. If you've got a lot of other instruments on site that are vibrating wire, these just couple into them. So there's not really any additional instrument or components that would be necessary. A lot of data logger manufacturers have devices and components that can read vibrating wire signals fairly easily these days. Something to consider when you're doing your design for strain gauge installations is, are these things going to be easily accessible, or are they going to be gone and irretrievable? If they're, on exterior mounted items, such as a bridge deck, you potentially could get back to them if something happens to them. Like I said, these have good longevity, recorded or records of good longevity associated with them. So, replacement just because they fail is typically not done, but oftentimes replacement's necessary if they get damaged from, something hitting them or something going on. Corrosion also can be influential in possibly replacing these if they're not installed correctly. So having an understanding of how to deal with potential replacements is a good idea. If they're not retrievable, such as they're in a pile or a pier or caisson or something that's going to be below ground, it's always a good idea to have maybe some redundancy associated with the installations. You may want to do that just to provide a balance on the installation, but also a little bit of insurance to make sure that it survives not only the driving, but the longevity of the monitoring program. So once you finished your design, you've made the order, these guys, your instruments come to you in several boxes. What you want to do is you want to make sure that you read through these things or look through the boxes and do a installation pre-check, I guess. You want to open up the boxes, especially if you receive a box that looks like this. You want to make sure that you open these things up and inspect everything, make sure that there's no physical damage to the instruments or the components that you ordered. This is the time to make it right. If something happened during shipping, let us know and we can work with you to see if we can get that resolved and get you replacements if necessary. You don't want to wait to the last minute to the day you're doing the installation to say, oh, we need to get this resolved. You also want to open up all the containers and check against what was ordered. Make sure that you've got the quantities and the type of items that you ordered, as well as the cable lengths. Make sure that those are all correct. And then any accessories that were ordered to help out with the installation process. Make sure that those are all contained in the shipping boxes. Typically, we provide some of that spray-in foam to kind of help seal everything in place and help protect it during shipping. So if there's small items that are shipped, sometimes, and we try to not make it happen, but sometimes those get embedded within the foam. If you're missing something, dig a little bit around in that shipping foam to see if you can find it. Another thing to do before you do the installation, and maybe right after you receive these, is to do basically a pre-installation acceptance test where you connect your instruments to a handheld readout device to see and make sure that you're getting readings. And then you could also apply a little bit of force to the ends of the strain gauges to see the changes in conditions to make sure they're responding as well. So that's very important. If these things aren't working when you receive them, give us a call and we can see if we can make that right before you get out to the site and start doing the installation. So to do that pre-installation testing and even do the installation correctly, it's not a bad idea to have handheld readouts to do that. We offer a couple of them here in-house. The GK404 on the left is a simple vibrating wire readout that provides output in digits, which is frequency-based, or hertz, or microstrain, which is typically used for the strain gauges. It doesn't save any data to it. It's basically a readout device that tells you what it's reading. So you could basically jot your information down on a field notebook or something like that. On the right is the GK406. That's more of a advanced handheld data logger, or not data logger readout. It's used for it's a great tool for diagnostics. It can store data. It can convert the raw readings into engineering units if necessary. And it can create a PDF report of your reading showing the diagnostics of that instrument, such as decay ratio, all kinds of other information that may or may not be useful. But if you're troubleshooting an instrument, it's not a bad tool to have. If you're just trying to get readings, the GK404 on the left is kind of the way to go. So let's talk a little bit about the strain gauges themselves, and we'll start with the surface mount strain gauges. We have a couple of those to offer, and the first one shown here is the Model 4000. Its standard gauge length is 150 millimeters or 6 inches, and our standard measurement range is the 3000 microstrain. We do offer various options or alternatives to this standard gauge length, and also the range. We can offer 5,000 or 10,000 microstrain range as well as an alternative. To do the installations, because this is it's basically called an arc weldable strain gauge, and the reason it's called that is because that's how it's typically adhered to a surface, and it's typically mounted on a steel element. To do that, you would basically have these end blocks, and you wouldn't install the vibrating wire assembly and tube yet, but you would use what's called a spacer bar and a spacer jig. With that spacer bar, that helps align the mounting blocks on either end parallel to each other and at the right distance. And so you secure the mounting blocks to that spacer bar, hold it up against your structural element, and then using an arc welding method, apply a weld along the top and bottom of each of these end blocks. You don't want to go around the end, because sometimes those welds will get too thick and block passage, so you couldn't get the spacer bar out and not get the instrument installed either. Here's an image of an installed Model 4000 strain gauge on a pipe pile, and most likely there's probably another one on the opposing side of the pile, or maybe even 4 total on this pile in each quadrant. This is installed along the axis of the pile, and it's likely 2 more strain gauges at least below this one, because you've got the signal cable routing through here. So you can see, if you look closely, you can see the welds on these end blocks that were done, And afterwards, they actually painted the weld and the end blocks with a black primer to help provide some additional corrosion protection. After these blocks were installed, they removed the spacer bar and installed the vibrating wire tube and then the coil assembly, and then routed that signal cable back up to this thing here. They've got these angle irons welded along the pipe over the axis of where these things are installed to protect not only the gauges, but the instrument cables as well during the pile driving. Once these things were installed, they've got a little section of steel that's going to be welded in here to kind of help protect the gauge during that process. Another option for installation, if you've got a concrete element and you want to use these Model 4000 strain gauges, is to use these epoxy groutable anchors with the end blocks attached to a little stub of thread bar. And so using this installation method, you would basically have a template that has two holes where the hole should be drilled, and you'd put that template on the surface, paint those or mark them, and pull the template off, drill the holes to the depth indicated. Then you'd use your spacer bar and your spacer template, attach those end blocks kind of with the bars, the anchor bars laying down sideways. So you get that way you could get the end blocks positioned at the right distance and also parallel to each other. Once those are locked into that spacer bar, you fill the holes with epoxy and then push these down inside of the epoxy and let that set up. Once it sets, you can remove the spacer bar from those end blocks and then reinstall your instrument in there and you're good to go. Another type of adherence or way to mount these things would be using epoxy. We don't really recommend or suggest using epoxy unless it's a short-term application, because epoxy can have a tendency to creep over time. And it's best if you can use either the weld process or the epoxy type of anchors that kind of mount into the structure. If it's just a surface, there's some instances where the owner may not allow you to drill into them, like if it's a historical masonry structure. And in those instances, you may want to use this if it's just for short-term applications. The Geocon underwater epoxy here shown on the lower left is a great epoxy system. It's basically a paste that you mix up in two parts, but once it sets, it's like steel almost. But again, for short-term applications. Some of the applications we talked about, like for braced excavations, there's a lot of internal struts shown here. Typically, you've got struts that go across the excavation to kind of help restrain it from lateral movement. You've got the soldier piles or secant piles on the sides to help restrain the soil on the sides, and then the open excavation. If you can't put tiebacks in through these to hold it back, you've got internal struts. So these internal struts can be instrumented with strain gauges to help monitor the increased load on the struts, to make sure you're not exceeding the capacity of the struts, and then also to monitor for potential deformation of the walls. If you start seeing strains increasing in these struts, it could be that the walls are moving in. You wouldn't know which side the wall's moving in, unfortunately, unless you've coupled it with inclinometers in the side walls to help indicate which wall's moving, this side or the right side. So that's one method of using. And like I talked about before, typically you would put strain gauges on both sides of the web to kind of help balance for any bending moments that might be occurring. Another type of typical application we've talked about already, driven piles, like steel piles, steel pipe piles, or H-beam piles is shown here in the picture. In this image on the left, they've got one strain gauge here, they've got another one further down, and probably another one down where this person's working. They've already been, the end blocks have already been welded in place, and they've got the wire tube portion attached temporarily there until they get the coil assembly and start routing the signal cables. They've got some blocks every 10 feet or so welded as well to kind of help secure the cable. And that's done just to kind of help keep the cable from flopping around during the driving activities. As it's very likely, and hopefully done so in this picture, that they've installed a mirrored section of strain gauges on the back side of this pile as well on this web. And then they've put this steel cover over this, the alignment of the gauges and the signal cables to help protect them during the driving process. I believe they cut a little window out here to kind of help with the installation of the gauge and making sure it's all set right, and then they'll put a plate over the top of that to cover that up during the driving. The other type of strain gauges that are surface mount are the smaller spot weldable strain gauges. And these are typically, excuse me, a 50 millimeter gauge length. They also have a 3000 microstrain range, which is, we can possibly, I believe we also have 5,000 and 10,000 microstrain range in these as well is an option. But the standard one is 3,000 microstrain range, which is typically more than sufficient for most needs. The spot welder is basically called electro or capacitive discharge welder, and it produces a low energy dimple basically between the tab on the strain gauge, this tab right here, between that strain gauge tab and the surface, which is more often than not steel. So you're just basically creating a little dimple and a series of dimples to help bond this strain gauge to the surface of the steel. Again, very low energy, it's 20 to 40 watt seconds of energy created. These things are often used in like pipelines, bridge deck girders, locations where you can't put the bigger strain gauge in. It takes a little bit more time to do these installs than the arc weldable, but there are certain applications where this might be better suited than the 4000. There's two types of these spot weldable ones. There's the model 4000 shown here. That's basically got a cover, or the coil assemblies built into the cover, and the signal cable's integral with the cover and the coil assembly, and this gets placed over a bare assembly that has just the wire tube in it and the end blocks. The other model is the 4150 shown here on the left. 4150 shown on here on the left, and that one has the coil assembly wrapped around the wire tube already that comes from the factory that way, and then you got the small leads coming out that transition into the regular signal cable. The benefits of one versus the other, time-wise, it might take less time to install the 4100 with the cover already installed here, but sometimes there's alignment issues with getting this cover positioned correctly over the wire tube, and you may not get the readings all the time. More often than not, it works very effectively, but sometimes we've had issues where they didn't quite get lined up correctly, and so there was problems with the readings occurring. This one the 4150 takes a little bit more time and finesse, but as with any good project, the more time you spend on it, sometimes the better results you get. One of the installation tools that you need with both of these devices is this alignment installation tool. Basically, you hold this down while you're doing the welding, and what this does is it keeps both end blocks aligned with each other and also provides downward force to keep everything kind of positioned while you're performing the spot welds. To do the installations of these spot weldable strain gauges is very, very important that the underlying surface is prepared effectively beforehand. This means the surface should be clean, dry, flat, and free of any rust, grease, or pitting. So it takes a fair amount of time to prep the surfaces, make sure it's all prepped and ready to go. One of the benefits of this system is that we provide, when you order these things, we provide a bunch of test strips so that you can spend some time getting yourself familiar with the spot welder and the particular subsurface that you're working with. Sometimes the energy at one site might differ from another application. So you spend a little bit of time getting used to the welder and the material that you're using and the material you're adhering to before you actually get into the production mode with these strain gauges. The manual for these strain gauges shows very well the process and the sequence of making the welds, but shown here, you can see some of the dimples. If you zoom in or if you look close enough, you can see the dimples on the tabs associated with this strain gauge. And those come from the manufacturer, from us, with them kind of pre-dimpled. But that's where you would start with putting the spot welder, and you start at the back end of one side of the strain gauge while you're holding the alignment tool, which he's not, unfortunately. But to be honest, he's already got the tabs welded. Right now he's putting a collar on, but we'll get to that shortly. But while you're holding the alignment tool, you'd start at this back end of one end of the gauge, and you hold the spot welder and apply the dots. You just move from one to the next, and then go from along the side and then to the top. And you complete the one row around each end, and then you probably would do a second row as well to just ensure you've got good connection to that subsurface. It's important to note before you move on to the second end, the other end of the gauge, is that these do have the capability of being adjusted. They come from the factory set at mid-range, which is around 2,500 microstrain. But if you need to adjust it one way or the other, you can do it before you weld, or you can do it after the first weld is complete, but you can never adjust that nut. And we'll show you shortly in another image of how you adjust that nut. Don't ever adjust it after you start welding the second end, the other end of the gauge, because you'll damage the instrument. So that you've got the tabs welded on the first end. While holding the alignment tool, you start the welding on the second end as well, following the same process. And once you get those tabs both welded together, then you do what they're doing here. They've put a collar strip. You can see it's basically hanging off this other end, but basically a collar strip over both ends to help secure that and help provide additional connection to the subsurface. After the collar strips are welded in, you put a little cover over this gauge, which basically is like a little half round, and then some collar strips again over that to hold it in place. Then you tuck in the wire into the cover, and then you put a little strip over the signal cable to kind of hold it in place so it doesn't pull that cable out from the instrument if anybody puts some force on it. So it's a little more of a process than the arc weldable, as you can see and hear, but it does provide good results over that 2-inch range. Here's a depiction of the installation of the 4100, the one with the cover built in, on the underside of a bridge deck. You can see they prepped the surface and cleaned it up nicely. They've got the location marked, and then now they're putting the strip over the cover to kind of hold it in place. So those were the surface mount strain gauges, and now we'll move on to the embedment type. Embedment type is obviously typically used with concrete because we can't embed these within steel very easily. So shown here is our standard model 4200. There's a large variety of different embedment type of gauges, but this is the standard one that's used for most type embedment gauges. It's a 6-inch gauge. It's got a lot of similarities to the 4000 6-inch gauge with the wire tube and the coil assembly looking very similar. This does have a sheathing over the wire tubing to provide a bond breaker in the embedment zone. Also, you've got discs on the ends of this instrument that help kind of lock it into the concrete when it's poured in place. Again, this model is 6 inches or 150 millimeters, and it's also got a 3000 microstrain range. There are other options if necessary or if needed to increase that microstrain range if you would like. Another type is a little bit more rugged, is our ruggedized embedment strain gauge. It's basically a 10-inch gauge. We have other ones that are larger in length that provide the same kind of microstrain range, 3,000 microstrain. This one's designed for use in large pores where you've got aggregate that might be 3/4 inch diameter or larger. The signal cable's actually integrally attached inside of this, so you don't have the little tiny coil assembly or loose wires. So it's a little bit more rugged and a little bit more expensive. On the other end of the spectrum, you've got the small miniature embedment strain gauge, and this is a 2-inch gauge range. It's very similar to the model 4150 with the little coil assembly over the center of the wire tube. On the ends of that 4150, however, you've got the discs that are used for embedment. This type of gauge is typically used in like laboratory testing applications, or in zones or areas where you can't fit the standard 6-inch standard embedment gauge. It's a little bit more delicate, so it's not recommended in most applications, but if you absolutely have to use it, it's available for that use. These embedment gauges do have the capability of being adjusted, like I mentioned before. They come preset at mid-range around 2,500 microstrain. If you want to set them plus or minus that, with the standard 4,200 embedment gauge, you can just hold the collar, which is like a little fattened end of the wire tube, and then while you're holding that, you can twist the round disc at the end while you've got it connected to a readout to ensure you're getting it to the value you want it to be set at. For adjusting the smaller micro or miniature gauge, and also the 4150, which I mentioned previously, you can adjust. You would basically hold the center of that instrument where it says center, and using a small tiny wrench, if you've got one that small, you can adjust that tensioning nut, again, while you've got it connected to the readout to ensure you're not going to overrange it and you can get it to the position that you desire. For mounting these strain gauges, these embedment strain gauges within the concrete elements, you probably need a variety of tools that typically aren't provided by Geocon, but you can pick them up pretty easily. Zip ties or wire tie for bonding or securing things, and then standoff blocks, either foam or wood. And the standoff blocks are necessary because what you want to do when you install these and you're attaching them directly to a reinforcement element is you do not want these end discs to be touching anything else. They need to be kind of free and exposed so that they lock into the concrete and they're not having any external lateral forces on them from the reinforcement or restricting them from movement. So using the standoff blocks, as mentioned previously, or Geocon does provide these nice little plastic saddles, they're called, that the gauges can sit on and then straddle the reinforcement, and then with a zip tie kind of hold it in position parallel to the reinforcement, and then at a distance sufficient enough to keep it clear from the rebar. So a variety of different ways to install them. Another option that's not shown here is if you want to center this embedment gauge between two reinforcement elements, is that you can tie off a steel wire to one piece of reinforcement, take it out, and then wrap it around the top of this strain gauge, and then extend that wire over to the next piece of reinforcement, and do the same thing at the bottom. And that kind of centers that embedment gauge between those two pieces of rebar. And if you need to tighten it up, you can take a piece of small pliers and twist the wire that's kind of securing it between the reinforcements to tighten up that suspension. As an alternative to the concrete embedment gauges we've shown, there's the rebar strain meter, or affectionately known as the sister bar. The sister bar gets its names because you're basically going to sister this up to an existing piece of rebar or reinforcement steel in the concrete element. The strain gauge is within the center of this sister bar. The strain gauge is attached to some steel component that is then welded to ends of rebar to help create this length of sister bar. And typically that length is about 36 inches. It's a 1/2 inch diameter bar, or number 4 rebar. Again, 36 inches in length, and the length is required to help develop the bond length for the reinforcement, to ensure encapsulation within the concrete, but also develop that bond length that's typically necessary over a certain distance. An alternative to the standard sister bar is what we affectionately call as the brother bar. This one can be any size rebar that you want, depending on your application. The idea with the brother bar is that this one is actually in line with the reinforcement you have. So you'd cut out a section of existing reinforcing in your cage or something like that. So you've got number 8 bars, you cut out the length that would appropriately fit this brother bar, which we're showing here is 43.5 inches. And this brother bar would be welded in place in line with the existing reinforcement to provide strain gauge monitoring in line with the existing reinforcement. And whether you do this or the sister bar, it's really up to you. Both ways are effective. When you do the welding, you have to make sure it's a very competent weld, and it's a complete weld that makes sure it's not going to break during any loading. The length is longer because you don't want to transmit the heat from the welding to that instrument and damage it in the center there. So that's why it's almost 4 feet long. When you're installing the sister bars, or the smaller diameter bars, excuse me, those kind of get nestled in to any corners or crooks, kind of out of the way of where you might be moving materials in and out of the hole. If this is like a concrete pier, and you got a big rebar cage, and you're going to be, lowering a trimming pipe in and out, you want that sister bar and the signal cable kind of out of the way. So you kind of hide it as best you can off to the side of vertical members, and keep it away from, like the vibratory equipment that might be used in the hole as well. Typically, we recommend that you'd have straps at about 1 foot away from the center on both ends, and then a few inches in from the end of the sister bar. And you can use zip ties or the steel wire ties as well. For the signal cables going up the pipe or up the reinforcement, we would highly recommend just using the zip ties, not use the steel, because the steel can cut into the cable. For the brother bar, the one that's in line, basically you need somebody that knows what they're doing as far as welding. And again, those go in line. You keep the cable out of the way during the welding process, and make sure that you don't damage that the signal cable or the instrument during the welding process. A little bit about the calibrations now. Most of our strain gauges, like the 4000s, the 4150s, 4200s, those are all shipped with what's called a batch calibration sheet. So you won't have individual calibrations, you won't have serial numbers associated with those gauges. Basically, we take a big batch of these instruments and test them and determine one factor that's pretty much applicable to all, and it doesn't vary by much, and so that's why we use the batch factor. It's fairly consistent throughout many of these batches. We check it periodically. If any changes happen over time, we'll adjust that batch factor periodically, but for the most part, it's been fairly consistent throughout the years. So with those calculations, it's much like any of our other instruments. If you guys are familiar with like piezometers, you take a reading, your zero reading, your current reading minus your zero reading times that batch factor will give you the change in strain in your measurements. So again, as we've always tried to push hard on folks, taking your zero rating is very critical. That's your baseline against what everything else is compared. The sister bars, however, are individually calibrated. That's the one exception. The sister bars are individually calibrated, and if you would prefer, instead of having a batch factor, you can have your strain gauges individually calibrated as well. at an additional cost. But if in those cases, you would get an individual calibration report for each instrument. The sister bars will definitely always have their own individual calibration sheet. They're loaded in tension up to about 6,000 pounds. The readings are typically an output in microstrain. So from that, you get a linear gauge factor in microstrain per digit. Similar to what was described before, to get your calculated strain or change in strain, you'd have a 0 reading, your current reading, multiply it times that gauge factor to get your change in strain. And with that, I think I'm wrapping it up. And I'm going to turn it back over to Joelle.
Thank you, Rob. Any support that you might need after this webinar, we just have some email addresses and some places to direct you. We have our sales team if you need any kind of pricing, support on an order, or if you're working on a project and you need some help with instrumentation and some pricing, feel free to reach out to our sales team. Technical support, if you already have our sensors, strain gauges, or anything else, we have support at geocon.com. You can reach out to them for installation support, configuration, or if you have anything in place already that's giving you some heartache, we can do troubleshooting with you as well. There is training with Geocon. We have some set courses that we do throughout the year. We have one coming up in October here, covering piezos, strain gauges, further in depth, extensometers, and then our inclinometer immersion course. We also offer custom training. If you have instruments that fall outside those parameters, we're happy to set up virtual training on a particular project or installation that you might have questions on. And so from here, we will move into our question and answer session. Right now, we only have a couple of questions. So if you have anything on your mind, feel free to type those in now. So we have, is there any maintenance required on the vibrating wire instrument?
As far as maintaining these instruments, if for like surface mount instruments, surface mount strain gauges, it's a good idea if they're still accessible to periodically check for corrosion. Obviously, you want to try to prevent the development of corrosion because that can affect the performance. But besides that, really no maintenance is involved. I mean, we don't need to have these sent back for periodically checked or periodic checks or recalibration or anything like that. And obviously, if these are installed below ground, there's no way you're going to retrieve these to service them again. So for the most part, you set them and forget them, or at least measure them.
Can these strain gauges be used for dynamic testing?
Yes. Traditionally, vibrating wire signals have been used for static monitoring, but more and more the vibrating wire signals can be used in dynamic applications as long as you've got the right devices to do that with. And typically these are like Campbell Scientific data logger components. There's a specific device, I think it's called the V-wire, that can be used to integrate with the vibrating wire signals to provide dynamic output for the strain gauges, vibrating wire strain gauges.
Is there an advantage to the batch calibrations versus individual calibrations?
You really don't gain a lot from the individual. You might improve your accuracy a very little amount, but what you're looking for is changes in the strain, and the batch calibration factor will probably get you more than what you're looking for, sufficiently enough. The individual calibrations may improve it slightly, but I don't think the cost and the time involved with it would probably be necessary to get much more out of it, to be honest.
Yeah, that is an important point too, is the batch calibration does help keep the cost of the gauge down once you individually calibrate or elect to individually calibrate a batch calibrated sensor, there is an additional cost associated with that typically. Do you experience some drifts linked to the wire clamps inside the gauge over time?
Good question. Those wire grips have improved over time throughout the years. There was, back in the day, some issues with drift, and over the years, not only Geocon but other manufacturers have improved their process of making those grips. And so these days, and probably for the last decade or maybe even 20 years, the process of getting those grips installed has improved to the point where you see very, very negligible drift at all, if at all.
All right, that looks like all the questions that we had come through. One note I will make before we wrap this up is we do have some videos available on our website that demonstrate the installation process for the arc weldable and the spot weldable strain gauge. So if you're interested in, being able to watch that process all the way through a little further than what Rob described here today, check out the video tab on our website and you'll see strain gauge videos right under that. And they're available for free if you want to check them out. But otherwise, we'll just wrap it up. Thank you so much for taking the time to join us for our discussion on strain gauges today. And we hope that we will see you again later this year for extensometers. And have a good one, wherever you may be.